filling the volume of space. And so if you make the volume of space twice as big, you get twice as many degrees of freedom. And so the entropy gets twice as big.
My title is technically computer scientist, computer analytics scientist, right? But I want to move that up to doctor in something, right?
So if you say that the entropy goes like the area
that'd be nice.
of a region, you're saying that the number of degrees of freedom is actually less than what you would have expected from locality in quantum field theory. But if you think back to what I said before, that's potentially catastrophic, because that means somehow the degrees of freedom here in my office can't really be independent from the degrees of freedom where you are. And if they aren't, then maybe we can communicate. Maybe.
Well, okay.
If I do just the right measurement here in my office, I can send you a message without having to wait for the light travel time in between. And so 't Hooft and Susskind proposed to just run with this and say, really, you don't have these independent degrees of freedom at each point in space. All the degrees of freedom are just living on the horizon of the black hole. Okay. But then it gets really crazy, because you can say, okay, well, we could be inside a really big black hole, right? And we wouldn't even know, right? The infalling shell hasn't reached us yet. It's going to reach us in 10 billion years. Could be true. There are certainly solutions of Einstein equation like that. And that would mean our degrees of freedom right here are really living out on some huge horizon surface out near spatial infinity. And the natural limit of that process is just that all the degrees of freedom of the system are always living off in spatial infinity. So we think we have all these independent degrees of freedom here and there and so on, but it's fake. And so what that means is that the very nature of space, where we think I have independent stuff that could be here, independent stuff that could be there, is emergent. It's not really correct. That the fundamental description of what's going on is you have this theory living off at spatial infinity. And it's only in certain situations and in some approximation that we can think that the degrees of freedom near me and near you are independent. And you see, as soon as we say that, we're now getting hints of what the resolution to the paradox might be. Because if what's going on near the horizon where the Hawking radiation is being produced isn't really independent from deep inside, where the matter is that you collapse to form the black hole, then maybe there is a way for the information to get out. And so that's kind of the direction that things have gone, in the last, say 30 years since these papers of 't Hooft and Susskind.
Right. Yeah. Okay, look, what he's trying to say is that we can throw into a black hole, we can throw a blue packet of chips, a green pair of shoes, and a yellow backpack, right? We're able to tell that there's a bag, a pair of shoes, and a packet of chips, a packet of crisp, or whatever, but we can't tell what color they are, right?
Right. So that's this holographic.
Yeah, that's this idea of the holographic principle, right? So that was the term Lenny used for this idea that all the degrees of freedom live at the boundary. That's what happens in a hologram. You have a sort of two-dimensional image of a three-dimensional thing.
The holographic principle was 6 years of my life.
And so Lenny proposed Lenny proposed the name, Lenny and 't Hooft proposed the idea that, really the way quantum gravity should work is you have this radical reduction in the number of degrees of freedom where the real theory is living at the boundary in this holographic sense.
And so
that's right. And that entropy at some point must remain constant.
This is a completely unfair and off-topic question, but maybe 30 seconds. Why would it be the case that we, cognizant beings, know about sort of this somewhat secondary or false picture